Yo, what's up everybody? It's Pankaj here. Welcome back to the channel where we break down complex tech concepts and make them crystal clear. Today, we're diving deep into the world of machine learning, specifically classification models. Now, if you've ever wondered how Spotify recommends music you'll actually like, or how Gmail filters out spam so effectively, it all boils down to classification models. These models are the backbone of countless applications we use every single day. And the craziest part is, they're not as complicated as you might think. So, whether you're a tech enthusiast, a budding data scientist, or just curious about the AI that powers our world, stick around because we're about to demystify classification models and give you the knowledge to understand their power. Let's get into it. Alright, kicking things off, we have logistic regression. Now, don't let the name fool you. It's not about predicting numbers on a spreadsheet. Despite the word regression, logistic regression is actually a powerhouse when it comes to classification tasks. Especially when you're dealing with just two possible outcomes. We call that binary classification. Think of it like this. Imagine you're training an AI to tell the difference between pictures of cats and dogs. You feed it tons of images, each labeled as either cat or dog. Logistic regression steps in and figures out a way to draw a line. Well, not literally a line, more like a decision boundary that separates the cat images from the dog images. The beauty of logistic regression lies in its simplicity. It's like the minimalist apartment of machine learning models, clean, efficient, and easy to understand. You can actually peek under the hood and see how it's making its decisions, which is super valuable when you need to explain the AI's thought process. Plus, it's computationally light, meaning it won't hog your computer's resources like some of the more complex models we'll talk about later. This makes it perfect for quick and dirty classification tasks, especially when you're working with limited data. Now you might be thinking, if it's so simple, can it really handle real-world problems? And the answer is a resounding yes. Logistic regression is used everywhere, from predicting whether a customer will click on an ad to detecting fraudulent transactions. It's the go-to model when you need a quick, interpretable, and reliable solution for binary classification. So, next time you see a spam filter doing its magic, there's a good chance logistic regression is working behind the scenes. Next up, let's talk about decision trees. Now, these models are all about making decisions in a way that's super intuitive, almost like how we humans think. Imagine you're trying to decide what phone to buy. You might consider things like the camera, the processor, the battery life, and of course, the price. A decision tree works in a similar way. It takes your data and splits it into branches based on different conditions. Each branch represents a decision, and each leaf node at the end of the branches represents a final outcome or prediction. So going back to our phone example, the tree might first split based on price. Phones below a certain price go one way, and more expensive ones go another. Then it might branch further based on camera quality, processor speed, and so on. The cool thing about decision trees is that they're incredibly easy to visualize. You can literally draw out the tree and see the decision-making process unfold right in front of your eyes. This makes them super interpretable even for people who aren't data scientists. Plus, they can handle both categorical data like phone brands or colors and numerical data like price or screen size. This makes them incredibly versatile for a wide range of classification problems. However, decision trees do have a tendency to overfit, which means they can sometimes get a little too specific to the data they're trained on and might not generalize well to new unseen data. But don't worry, we'll talk about ways to combat that in a bit. Overall, decision trees are a great choice when you need a model that's easy to understand, visualize, and explain. They're like the flowcharts of machine learning, guiding you through the decision-making process step by step. Now let's step it up a notch and talk about random forests. Remember how we said decision trees can sometimes overfit? Well, random forests are here to save the day. Think of a random forest like a team of expert decision makers, each with their own unique perspective. Instead of relying on just one decision tree, a random forest combines the predictions of multiple trees to make a final, more robust decision. It's like getting a second, third, or even 100th opinion before making a big call. This ensemble approach helps to reduce overfitting and improve the model's overall accuracy. Here's how it works. The random forest algorithm randomly selects subsets of the data and features to create multiple decision trees. Each tree is trained on a different slice of the data, so they all learn slightly different patterns. Then, when it's time to make a prediction, all the trees in the forest cast their votes, and the majority vote wins. This voting mechanism helps to balance out any individual biases or errors that might exist in any single tree. The result is a more accurate and reliable model that's less prone to overfitting. Random forests are like the Avengers of machine learning, a team of powerful models working together to achieve a common goal. They're widely used in industries like finance, healthcare, and e-commerce for tasks like fraud detection, disease prediction, and personalized recommendations. So, if you're dealing with a complex classification problem and need a model that's both accurate and robust, random forests are definitely worth considering. Alright, moving on to a slightly more advanced but equally fascinating model, support vector machines, or SVMs for short. Now, SVMs are like the master swordsmen of the machine learning world, precise, elegant, and incredibly effective. They excel at finding the optimal boundary that separates different categories in your data. Imagine you have two groups of data points on a graph, and you want to draw a line that perfectly separates them. An SVM would find the line that maximizes the margin, or the distance between the line and the closest data points from each category. This line is called the hyperplane, and it's what the SVM uses to classify new, unseen data points. But here's the really cool part. SVMs can handle situations where the data isn't linearly separable, meaning you can't draw a straight line to divide the categories. They do this by using a clever trick called the kernel trick, which essentially transforms the data into a higher dimensional space where it becomes linearly separable. It's like adding an extra dimension to your graph, so instead of a line, you can now draw a plane or even a more complex shape to separate the data. This makes SVMs incredibly powerful for tackling complex classification problems with nonlinear patterns. They're particularly well suited for tasks where you need a high level of accuracy and you're dealing with high-dimensional data like images, text, or genomic data. So, if you're looking for a model that's both accurate and capable of handling complex data, SVMs are definitely a top contender. And, last but certainly not least, we have the rock stars of the machine learning world. Neural networks. These models are inspired by the structure and function of the human brain, and they're capable of learning incredibly complex patterns from data. Imagine a network of interconnected nodes, organized in layers. Each node receives input from the nodes in the layer below, performs a simple calculation, and passes the output to the nodes in the layer above. This layered structure allows neural networks to learn hierarchical representations of data, meaning they can detect simple features in the lower layers and combine them to recognize more complex patterns as you move up the layers. It's like starting with recognizing edges and lines in an image and gradually building up to identifying objects, faces, and even emotions. Neural networks are incredibly powerful and have revolutionized fields like computer vision, natural language processing, and speech recognition. They're the driving force behind technologies like self-driving cars, facial recognition software, and virtual assistants like Siri and Alexa. However, this power comes at a cost. Neural networks are notoriously complex to train. They require massive amounts of data and computational resources, and fine-tuning their parameters can be quite challenging. But when it comes to tackling the most challenging AI problems, neural networks are often the go-to solution. They're like the supercomputers of the machine learning world, capable of learning and adapting in ways that continue to amaze us. So there you have it, guys, a crash course on classification models in machine learning. We've covered a lot of ground today, from the simplicity of logistic regression to the mind-blowing power of neural networks. Remember, the best model for your specific task will depend on factors like the size and complexity of your data, the desired accuracy, and the interpretability you need. If you're just starting out, logistic regression and decision trees are great places to begin. As you gain more experience, you can explore the power of random forests, SVMs, and neural networks.